Ever wondered how a simple cone can make your voice sound so massive? Well, there's some seriously clever physics packed inside a megaphone. And today, we're going to crack it open by tackling a real GCSE exam question, step by step. So let's dive right in.
A megaphone makes things louder. Yeah, we all know that. But how? That amazing journey from your voice to that booming sound, that's all pure physics. We're going to break it all down using an actual question from an AQA higher tier paper.
So our mission starts right at the beginning, capturing the sound. Before a megaphone can amplify anything, it has to convert your voice into a completely different form of energy, and that, my friends, is where the microphone comes in.
Okay, here it is, our first question from the paper. A little fill in the blank to get us started. We know sound waves are just pressure variations moving through the air, right? The microphone's job is to take those pressure variations and turn them into variations in, what do you think? And the answer, straight from the official mark scheme, gives you two options. You could write an electrical current, or you could write potential difference, which, is just another way of saying voltage. Either one gets you the mark, because they both describe how the microphone turns sound energy into electrical energy. That is the absolute key transformation. Okay, next up, we're looking at the magnet inside the loudspeaker. The question asks which diagram shows the magnetic field correctly. Now, there's one super simple rule you just have to remember. Magnetic field lines always go from north to south. If you just apply that one rule, you can see that the only one that works is the diagram in the top left. Easy peasy. The next part is a nice, straightforward definition for 1 mark. What exactly is an induced magnet? Well, it's pretty simple. It's just a material that starts acting like a magnet, but only when you put it inside another magnetic field. The second you take it away, poof, it stops being magnetic. All right, so we have successfully turned sound into an electrical signal, but that's only half the story. Now we've got to turn that signal back into sound, but way louder. And to do that, we need to create movement. This brings us to a really, really important concept in physics, the motor effect. Now take a look at this diagram. This right here is the heart of the loudspeaker. You've got a coil of wire sitting inside a permanent magnet's field. That electrical signal we made earlier, it gets sent through this coil as a current. And this is where the magic happens. When that current flows through the coil inside the magnetic field, the coil is forced to move. And what's the name for that amazing phenomenon? Well, that's the motor effect. It's the exact same principle that makes electric motors spin, and in our case, it's what makes the speaker cone vibrate back and forth to create those big, loud sound waves. Okay, deep breath. Now for the part that can sometimes trip people up, the big 4-mark calculation. This is where you have to prove you can apply the physics. But don't worry, we're going to break it down. Just remember, showing your work step by step is absolutely crucial for getting every single one of those marks. Let's walk through this together. Our goal is to find the magnetic flux density, which we call B. So step 1, pick the right equation from your sheet, and that's F equals BIL. Step 2, we need to get B by itself, so we rearrange the equation to B equals F divided by I times L. Now step 3, and listen up because this is the classic mistake, check your units. The current is in milliamps, so we have to convert 16 milliamps to 0.016 amps. Then, finally, step 4, just plug in the numbers and solve it. And after you've plugged all those numbers into your calculator, you get this, 0.125. But what's the unit? The unit for magnetic flux density is the Tesla. Yep, named after that Nikola Tesla, which we write with a capital T. So our final answer for all the marks is 0.125 T. So we've gone from sound to electricity and back to sound again. Phew. For the final part of this question, we're going to switch gears completely. We move away from the mechanics of the megaphone and into the human side of things, how we actually hear and what data can tell us about hearing loss. So what we have here is a graph that shows the quietest sound level 3 different people can hear across a whole range of frequencies. We've got person A, person B, and person C. The question asks us to compare how age, environment, and frequency affect their hearing. Now, to get the marks here, you have to be really systematic. So first, let's isolate the environment factor. We'll compare person A and person B. They're the same age, but A worked in a loud environment. And you can clearly see their line is much higher up the graph, which means they need louder sounds to be able to hear. Next, let's check out age by comparing B and C. Both worked in quiet places, but B is older and, yep, you guessed it, their line is higher too. They need a higher sound level. And finally, just look at the general trend for all three lines. As the frequency on the bottom axis goes up, all the lines go up. That tells us that everyone finds it harder to hear higher frequency sounds. So you can take all of that analysis and boil it down into one clear conclusion that would get you the final marks. Both age and working in a loud environment reduce a person's ability to hear. It perfectly wraps up everything that data is showing us. And there you have it. We have gone from sound waves to electrical current, used the motor effect to create actual movement, calculated a magnetic field, and even analyzed data on human hearing. That is the complete physics of a megaphone. Totally broken down. You've just mastered it. Nice work. So, I'll leave you with a final thought to chew on. We've seen how the motor effect is the absolute key to making a loudspeaker work. But this powerful principle of turning electricity into motion, it's literally everywhere. Where else in your own home does it power the things you use every single day? Have a think about it. Thanks for joining me.